Okay, so today's video is going to be about Pauli Exclusion Principle. Pauli Exclusion Principle. Exclusion Principle. Okay, so in quantum mechanics, or in particular, there are two types of particles: bosons and fermions. Okay, let me first go with the difference between what these two are. Boson has fermions have plus minus half spin. Bosons have, I think, integer spin. Integer spin. Okay. And the example of boson is photons. Okay. And for fermions, it's electrons. Acha. So then what we're talking about is in when if we have energy level like this, let's suppose if we have energy levels like this. Okay, this is for electron and this for photon. Sorry, here in photons, both particles can exist more than not like more than one. Like particles can exist in same energy level in multiple amounts. They don't have to be any specific amounts. They can be any amount. Okay, they don't have any limitations. Infinite amounts. Okay, okay, but for electrons, the problem is that for electrons they can only be two, and certain amount, the amount is specified depending on their properties, because for a particle to be in certain let's suppose this, if we have this, if we have a particle, let's suppose element calcium, it has 20, I think 20 elements. Okay, 20 electrons. So for it, let's suppose I'm taking an example, in its first shell only 2 electrons can be there, but again the criteria is that, and it is for any particle, the criteria is that both of these must have either one of these as different. This and orbitals or type, and what else, quantum number. Either one of these must be different for these two electrons to be in the same energy level, which is there, that these two electrons have opposite charges. Opposite charges. And what about the n? Energy level is nothing but, this is the energy level. This is energy level 1. This is energy level, and number 1, number 2. Okay, and this is number. And about other two, they're not that important in quantum mechanics, so we'll be ignoring them, or for this video ignoring them. Okay, so here the claim, what I'm saying is that it goes with any particles that two electrons or some certain amount of electrons can exist in the same state, but they must have different, either they must have different n number, quantum number, or they must have different spins, or they must have different type of orbital types, different they must have a specific orbital type, okay, and they must have a orbital type as well. Either these four, any one of them should be different in each group for each particle. Okay, now getting to the quantum mechanics of Pauli exclusion effect principle is that, let's suppose we have two particles, particle 1, particle we have not particle, we have uh, a box, okay, a, a box, or a what I would call, sorry, whatever you call it. Let's suppose we have an particle in it, okay, we have a particle inside it which is moving in x direction, okay. So in terms of waves or graph, we will make it as like this. This will be our wave. This is the imaginary part function, this is real function, and this is the wave. Here, note that this over here is a, here particle is in its lowest energy level, lowest energy level, okay. Here particle is in its lowest energy level. Then here we have, this is how the graph would look like, okay. And so this is what we call its wave function, okay. And how do we get this probability? Norm of wave, and this wave depends on the real wave function and the imaginary wave function. This wave will depend on those, okay. When we increase energy, we know that by equation, this equation, when we increase energy, the number of frequencies will increase, right? So here, let's imagine, before you doing that, let's go for two particles, okay. We will go for two particles, x1, x2. This is particle 1, particle 2. Now these two particles are in the same box. Like before we had only one, now we have two, but the property is that they're indistinguishable. Indistinguishable. They're indistinguishable, okay. Distinguishable. Oh sure. How can I not spell indistinguishable? Oh, different. Let's suppose we just write it's different, okay. Now here the problem or the thing here is that when they're indistinguishable, we would say that wave function A and wave function B at x1, sorry, x1 and x2, it should equal okay. So look at this, what we have here, the probability of wave, the probability of A at x1 and B at x2 is the same as probability of A at x2 and B at x1. So which will give us probability of A and probability of B equal to plus minus probability of this is what it should be looking like. Probability of plus either in the opposite, in the top one, either we have the sorry, what do you call this, Wait, let me get used to it. Before this we'll talk about wave function of the symmetrical and anti-symmetrical wave functions, how they look like. Okay, so when we talk about wave functions, when we talk about wave functions, they matter on what type of particle we are talking about. If we are talking about boson, it will be different. It will be different. By different, I mean it will be a symmetrical. It will be a symmetrical. And fermion, for fermion, it will be for fermion. It will be anti-spin, anti-symmetrical. Okay. Now, how? So, how do we do this? Okay, so here for these two, for boson and fermion, the wave function square, when we take it square, what do we get? Look at this. We get either positive or negative, either positive or negative wave function. Okay, so the positive part will be boson, and the negative part will be fermion. And so fermions are our main topic today. As per we have been discussing till now that they are why they exist in different things. So the wave functions for antisymmetrical will be that this and then this. Okay, this will be our antisymmetrical, and when we take it combined or combined over here, we get a different curves like this, and the probability of finding the finding probabilities x1 equals to x2 will be 0 as per this line over here. The line crossing, the amplitude is giving us 0 over here. And if we do the same for if we do the same for if we do the same for okay, so if we do the same for the what do you call this, sorry, now when we will draw the graph for now look at this. When we draw the graph, by the way, this is symmetry, this is simplicity, is not that into detail. I'm not drawing the different graphs, so it will take time. So over here what we see is that there is a probability when x1 is equal to x2, this is x2 x1, okay, real, imaginary. So I can write this over here symmetrical as 1 by 2 Because of it, let's put this is a particle. This is a particle which is um, spinning up and down. Okay, both. So I will write in terms of wave function. I will turn the wave function symmetrical. Symmetrical. What do you call this? Superposition state. Superposition state. Okay. So what I will write is 1 by square root of 2 up down plus 1 by square root of 2 down up, okay, equals to spin. This will be our for symmetrical, and yes, for anti-symmetrical it will be negative 1 over 2 up down, negative 1 over 2 down up, equals to spin for anti. Okay, so what this over here says, over this one over here, or this one over here, or and this one over here, is that for negative, if we have two energy levels, energy level 1 and energy of 2 and energy level 1, so the chances of finding probability of finding these two electrons, finding probability of A being there and B equals B here, is equals to finding B on top and A on bottom. So it's interchangeable. Here we're not distinguishing. We are still not able to distinguish. Okay, and so what we say is uh, so okay, when we have a big wave function in the symmetrical, when we have a big wave function, because right now they're acting as one, so it will not, we will not have a problem in having many particles at one point. We can have many particles without having any problem or any issue in the wave function. It will cause no problem in the wave function. And so then, by the way, till now what we were doing is that we were ignoring all the forces which they are affecting on each other, they were ignored. Influencing forces influencing on each other were ignored. Okay, now, and wait, if I did clearly say that they, when we are talking about particle, more two particles and one, they are indistinguishable. So if we have particles, if we have two particles and one of them, what the, and so let's suppose if now what we have, one of the particles has more energy level. Okay, one of them has more energy level, and so what, in terms of wave function, we will write it as like this. Okay, this is first and this is second. Look, one of them is different, one of them has low and one of them high energy level as frequency is increased. That is how it's shown. It could either be because they're indistinguishable, we could make the same graph, and in this graph we will have what, now this will become this and this one will become the other graph. Even this is odd because they are indistinguishable, so both are fine. So this also tells us that no two fermions can occupy same quantum state. Okay. About the wave function, we all know that the wave functions exist in superposition state till we observe it, it breaks, and we have one single certain value. So this is what the equation was we were talking about. This equation says energy is directly proportional to frequency. Indistinguishable or indistinguishable also means that they are identical particles, so that's why we cannot distinguish. That's one reason for them to do it. And so in a symmetrical waves, what happens is that the waves on combining, they will reinforce each other and make a wave which is bigger in size. Bigger in size mean, by bigger in size mean they have more higher amplitude. Yes, amplitude. And this amplitude is nothing but wave function, which you can get by square root. That means finding particle here is 5%, here is higher 50%, or lower than that, here 2%. That's what the wave function is about. And so what else we have is that, okay, let's get a little bit of small amount of energy level. How to say this, how to write the levels. Okay, so if we have calcium which has 20 electrons, so how we write is that we have this energy over here, energy level, and we draw, okay, this is how it will be done. Sorry. So these are energy levels. This is 1s, 2s, this is 2p, this is 3s, this is 3p, 4s, and 4p. Now, so remember, they cannot have same state. They must be opposite. One is up, one is down. Because of different, because if they have same, that would break it, and we would have nothing. I'll talk about that later. Wait, sorry. The rule here is that there's a rule over here. For filling these three, we have to first complete for one state, and then we go for the other state. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 more to go. We just keep on putting arrows. 1, 2, 3, 4, 5, 6, 7, 8, and 9, 10. So it's 20 complete. So this is how you can write 20 electrons in terms of energy level, and these over here, the up arrow and the down arrow shows that these two electrons are different from each other as they have opposite spins. One is spin up, one is spin up, and one is spin down. And so this is how it this is what these are. And now we can even write what these are. So for them, to write what in terms of sentence, what I will write is, what I will write is 1s square. The square is the number of electrons. Then 2s square. Then 2p. 1, 2, 3, and then 6. The power here is defining the number of electrons in that state, and then 3s is 2, 3p is 6 again. How many is that? And 4s is 2. 2, 2, 4, 10, 2, 2, 4. Yeah, so this is how we can write it in sentence form. Okay, now one more interesting thing, the the phenomena or the real reason behind electrons not existing in same state, but if they have no difference, is that if they all the electrons exist in same state, there wouldn't be any chemistry, because chemistry works on transfer of electrons and ionization, something like that. Also, when there's no chemistry, there wouldn't be any life, and in life we are not existing right now. So there's a huge reasoning behind electrons not occupying same space on the condition that they have same properties. So then when we talk about let's summarize now. Let's summarize like what we talked about. We talked about that electrons or fermions in particular. And by the way, fermions are for matter, what makes up the matter, and that is what life is all about. And photons about interaction, or the bosons about interaction, forces. Okay, they must be for forces. Now, to summarize, we talked about that electrons can be two types of wave functions, symmetrical and anti-symmetrical. Symmetrical being that they can increase or they can reinforce each other and give us a bigger amplitude, and anti-symmetrical, they cut each other. They will give us one up and one down. They will be opposite moving wave functions. And again, it only happens when we have indistinguishable fermions or particles. The particles are indistinguishable. It will only work in that case. If it's distinguishable, we would know which one is which, and it wouldn't be it would confuse, or it would not have a good explanation. Yeah, that's it.